Hello everyone and welcome. In this lab, we are going to learn about supervised fine-tuning. Specifically, this lab is exactly the same as the previous lab, such that we are going to use a PubMed Q&A balanced dataset, which is only focusing on yes and maybe class. And as a backbone model, similar to the previous lab, we are going to use LLaMA 3 billion Instruct version of it. The only difference is that we are going to do fine-tuning, which is a process of updating the weight of a model using the training data which is labeled, to improve the performance on a specific task, which in this task would be biomedical question and answering task. If you look at the pipeline, it exactly remains the same as we are doing only off-the-shelf model. The only two steps that we need to consider here would be the compute of loss, which is a comparison between the ground truth and the output that the model give it to us, and gradient update. And based on the loss that we have, the weight of a model is updating. And during inference time, we have an access to the data which are not labeled. We consider that during this time that the model need to operate at wild. So we need to ensure that the training data is not exposed during inference time. Or it can be exposed, we should not use it as a kind of ground for assessment of our models, because it has been seen by the models here. And you can see that we are not doing any kind of weight update during inference time. We create a message and then the chat template, we conduct a tokenization, and we give it as a kind of model to our model, which is LLaMA in this case, and then we decode the output. The whole process, as I mentioned, remain the same, but we are going to cover a wide range of a topic here. We will learn about the baseline evaluation of a base model, which we have conducted in a previous lab. We will learn about the supervised fine-tuning, as I have also described here. We will learn about the low-rank adaptation, which is a parameter-efficient way of fine-tuning models. And also we will learn about the difference between LoRa and QLoRa, which is basically 4-bit training for fine-tuning in order to be able to fine-tune the model in accessible and limited hardware. And we'll learn about LoRa adapters, basically how we need to set the parameters there and how we would be able to save the model. We will learn about supervised fine-tuning trainer, which is a kind of model coming out of the toolbox that we have from transformer reinforcement learning libraries. We will learn about how to monitor the loss and evaluate the fine-tuned models, and have a kind of comparison compared to the previous lab. And at the end, we would be able to save and reload LoRa adapter that we are going to use for the next lab. It is important for this lab that we cover that you learn about lab 1, lab 2, lab 3, because there is a coherent continuity between these different labs, and obviously familiarity with the PubMed Q&A dataset is important for you to understand the lab in a better way. For this lab, I'm not using Google Colab. I'm using my local machine. However, you could run this code in an efficient way in Google Colab. So for PubMed Q&A dataset, you already, if you follow the past lab 3, I have provided comprehensive explanation about that. It consists of biomedical question and answering task, which is including like a scientific question, which often would be the rephrased version of a title of a medical articles. Then we have like a full context, which is extracted from background, method, and results. And as an output, we could have long answer and final decisions, which in this case, we are mostly focusing on yes and maybe. Long answer is a medical reasoning that can be extracted from conclusion of articles or the human written summary of finding. So I'm not going to run anything here. Everything has been run previously because the fine-tuning it takes some time, but all the code is available for you to be able to run it on your local machine, similar to the previous labs. So we have like the output of a model. You can see in reality how it looked like. Is a breast best for children with a family history of atopy, and like basically the final answer is yes, or it could be other question. It could be also maybe. I provide a deep dive explanation similar to that one in the lab 3. We have here 3 different class distribution, yes, maybe, and no. And we have done sample for sake of tutorial. We have done sample to 110 and 110 samples. In total, we have 220 samples here, which is evenly distributed between yes and maybe class. Then we need to check our environments to see that if you have access to torch, CUDA is available, and how much RAM we have available. Then after that, we need to load our model and tokenizer, similar to the previous labs, that we load our base model, which is LLaMA 3 billion Instruct version of it. And we have also a corresponding tokenizer to that. It is important to say that, well, for efficiency, we are loading in 4 bits. And that would be the base for us for training our model based on quantized LoRa or QLoRa. Because it makes our job easier for training our models. So what the next step is that we need to create a chat template. So we have a raw PubMed dataset. We create a message which is based on a system, user, and assistant message, and we bring it all of them into the chat templates, and so that we have a training ready data set. This is exactly similar to the previous lab. I gave a full explanation here in the previous lab. So the most important part here is that we need to ensure that we are not tokenizing. This variable, it has been set to false, and add generation prompt, it also set it to false, because neither we expect that the model would do any tokenization, nor we are expecting that the model give us any kind of response. And you can see that we have a system, which is our system prompt here. We call it your biomedical question answering, and answer exactly with one word, yes or maybe. And we have a user, which is our content informations, and the actual question and the context that we are providing to our model. And as a label, we already give to the model this final decision. So he said that, well, given this question and this context, the response would be yes, or given this question and the context, the response would be maybe. We provide such information to the model in order to be able to use those information for training purpose. So we create this chat template, as you can see here. We have a system prompt, we have a question, we have context, and we have a final response here. And after that, we are able to create a training and validation set. We didn't create any kind of test set only for demo purpose is fine, but it's important for production purpose. For picking the best model, you need to pick the model that is performing really well on a validation set, and use that whole that model for that checkpoint actually for deployment at a scale. So that part is already, so after that, we need to establish the baseline similar to the previous lab. This is only repetition, so I didn't want that the people switch between these two labs. The deep dive explanation has been provided for this part of a lab in the previous lab. If you're interested, you could review that. And after that, we need to predict that without any kind of fine-tuning. We see that With the 90% of cases, we are able to predict correctly, and maybe class is only 40%. That was a result of a previous lab. However, when I run it here, I see a slightly different, which I will show. Is it become like the number has been changed to 1 or 2% more, and is insignificant. But however, the theory that the conclusion that we take during previous lab, it remain it holds true still. It's the overall accuracy is improved to 54% anyway. So until this point is only repetition from the previous lab. So I highly encourage you to visit the previous lab, which is about why we need fine-tuning. The solution here is that we need to do a supervised fine-tuning here, and supervised fine-tuning, as I mentioned, it means that provide a couple of examples to the model to be able to get opportunity to learn about the style and the expectation that you have from a model in order to replicate, to know or replicate the format that we would like the model response to us. That's how we are able to do fine-tuning, and for doing that we can use LoRa, because it's basically help us to train the model in a more efficient way, so we do not need a significant amount of resources. And if you're really tight in your resource, for example, you have a Google Colab with 8 GB of VRAM, you definitely need to use a quantized version of LoRa, which would be our case here. So as I mentioned about the supervised fine-tuning, that would be the continuing model training on curated task-specific data set of labeled examples. So it could be, in our case, is a PubMed Q&A data set. As the input, we give a biomedical question and the context, and the output would be yes or maybe. And we use a cross-entropy loss for predicting label tokens. So as a LoRa, normally what we need to do for updating the weight, here it gets somehow technical. If you do not understand it, don't worry. I highly recommend that you revisit the legacy course from Andrew Ng on machine learning course. I think it's from 2010. Still, it never gets old. All the concept about like a fine-tuning weight update, it's coming from that lecture. It's very well explained. But anyway, in a high level, is basically once you are update the weight, you have the base model from weight you have the old weight from the base model, and you are trying to basically update that given the information, given the loss that we compute from the models. And we compute a new weight here. The major challenge is that if you want to update whole metrics and whole weights, it would be quite expensive. So for that reason, we are going to use a kind of approximation, which is basically a product of a two small matrix, which we call it B and A. A matrix would be input size multiplied by rank, which multiplied by R, which stands for rank, and B would be rank multiplied by output size. At the end, that would be a way smaller matrix, which is mounted on top of the frozen metric that we have here. So to give you a glimpse of how it look like is that if your original weight dimensions would be 4096, you need to multiply by matrix of 4096 by 4096. You have almost 17 million parameters to be able to update. However, with the rank of 16, what you would have, you would be able to reduce it significantly and reach to 130,000 parameters compared to 17 or 16 billion parameter, which shows that 128 times less. So obviously it came, as we are doing kind of approximations, it comes with a reduce in a performance, but we need to find a balance between efficiency and accuracy. And the rank play a significant role, because the larger rank you would have, the more parameter you would be able to update. So the capacity of a model will increase, and hopefully you will have better results. So there are a couple of other stuff here. So we'll have like a parameters here. We have like a scaling factors, and we have a capacity of model, which is R here, and target models, which is consisted of all attention and MLP layers. And we have LoRa dropout, as well as different parameters that is relevant to the honest slots. So these are the parameters that we are going to use. However, the important thing that we need to consider here is that we are going to use QLoRa. It just reduce the number of parameters. The important point is that as we have set it here, once we load your model, you load it in true, and all the other process will remain the same. Here we have a kind of estimate on how much you would be able to save. Here is that full fine-tuning, it will take you 48 gigabyte. With the brain float would be 24 gigabyte. With LoRa would be less, and with QLoRa would be even less than that. So once you apply LoRa on top of the adapter, you will see these things. So this is your attention, this is your transformer, which it consists of attention head and feed-forward networks. There are a couple of target points that need to be updated. You have a choice to update all of them, and you have a choice to remove some of them, because it's basically might be very much heavy for you. The red one, assuming that here we are going to update everything here. So the red one, the red box, is the LoRa target models that basically will give the permission to honest lot to be able to update all this weight. These weight Q, K, and V, they are attention mechanism, which is stand for query projection, key projection, and value projection. And after that, once we apply the attention mechanism, we will get the output, which is the output projection. The output projection will create a kind of output value is applied on top of the attention output, and then we use this output value as the input of feed-forward neural network here, which consists of gate projects, projection, up projections, and we have like an activation unit in order to add some nonlinearity to increase the capacity of model to be able to learn more, and also reducing some gradient vanish from the models, and make our model so more effective. And then we have like down projections. You can see that there are like some parameters remain untouched, because they are a core operation like add and norm that basically look at the it look like a ResNet architecture, the add part of it, and then we apply normalization to help the gradient flow effectively across transformer unit. So all of these process can be write in a single line of code. So we identify target models. We have a key proj, K proj, V proj, and O proj, and the same for MLP part, that the gate proj, up proj, and down proj. So I have played a little bit with these parameters. I see that with the lower amount of a 64, I'm not able to get a good result. So I keep the rank to a 64. You might not be able to run it. I'm not sure on Google Colab how it works, but I had no problem to run that configurations. So after that, what we need to do, we need to set up our supervised fine tuning trainer, which is a kind of a tool that is imported from transformer reinforcement learning, which is a popular, as I mentioned, in the Hugging Face library for training and aligning large or small language models. And we are going to use SFT or supervised fine-tuning config objects, and basically we are going to use also args elements here that we would be able to put some information about the training procedure that we would like to have. There are a couple of parameters here. We have a per device trained batch size, which is basically says that, well, we per each device we will have 2 batch size, and the gradient accumulation steps, it means that every 4 steps it needs to do the gradient computation. So in total, this combination will say will give this impression that our batch size would be 8. So they use kind of a trick to be able to make it efficient for running on a consumer computer during training. Then we have a warm-up steps that basically it helps the model to increase the level of of a learning rate in 5 steps to reach to its peaks, and after that it reduces to the lower levels. The maximum number of steps would be 175, or which is over with the 8, which would be with the 176 samples around 8 epochs. The learning rate is a standard here. We put it 2.2 10 minus 4, and logging a step would be in each step, just make the logging for us. As the optimizer, we are using Adam, but with the 8-bit, it would be even faster to train. Weight decay is a parameter that helps you to reduce the overfitting. As the number of data is low, we are basically using this number. Then in terms of data format and the precisions, we also have a possibility to set it up here. And at the end, we are able to, we keep the seed to 42, and if you're using the same computer, you would be able to reproduce your results, no matter how many times you would run the code. And then you have like a output directory where you save your models after training. So this is pretty much about that. You could see that we have run that. We have a training example of 176. Effective batch size would be 8, 2 per device, and 4 per gradient accumulation. And a step per epoch would be 22, and maximum number of steps is 175, as we have set. And here we start to run the trainer. We have a trainer.train, and we run the models, and we are looking at the loss value. You can see that initially the loss is high, and while we are going, we are increasing the number of epochs. We start to have a lower and lower number of loss that we have here. You can see we go down until we reach to, we start from 2.5 and we reach to 0.1. Because it makes sense, because after some time the model is start to learn and recognize what is the right answer given the training samples. However, we haven't done the test on the validations, because you would be in a practice, it's better to pick the model not based on the best or lowest amount of loss that you get on your training set, but rather the best model that you get on your validation set, because that's the data that was not exposed during the training. So let's look at the loss function here. You can see that this number start to increase initially. That could be a warm-up effect of a learning rate that it start to it has been like a it start from very low value, it reached to the peaks it start to decrease, learn about the data and instruction until we can see some stabilization after 125 or 150, I would say, steps, such that the model, it means that the model is not able to learn anything significant after these steps. So the other things is that after having this value in your hand, we are able to run that part, and we can see that the result that we are able to get with the fine-tuned models is 32 out of 44 compared to 24 out of 44. The accuracy boost has been somehow significant, from 72.7% up to 54.5%, and we had around 80% of accuracy. Now we are going over every class to see that how was operating compared to the previous times. You can see that the number of the positive class is significantly, again, is high, 86%, and the number of a maybe class is getting better. We reached to the 60%, and in average we are able to get 72%. So if you want to look what was the baseline compared to the previous time, you can see that yes class was 90%. After fine-tuning, we reached to 86%. It means that, you know, we sacrifice some of the performance here, because the model is start to learn about the maybe class, so it start to somehow just basically confuse between yes and maybe, and was uncertain about that. But you could see that compared to the previous one, which was 18%, it boosts to 60%. So it means that we are able to get 40% by fine-tuning the models. Obviously, given the number of samples that we have here, is not really conclusive, because having more sample would help us to be able to predict maybe better output. The overall accuracy, as you can see here, is 50%. It boosts to 72%. So it means that we are able to close the gap significantly. Still is not perfect, and we require maybe more data and more instructions. So that is pretty much about this lab. So at the end, what we have learned here is that fine-tuning, it supports us to be able to learn about the domain-specific adaptations on a highly specialized task. Obviously, the quality of fine-tuning would be highly related to the quality of data that we have. At the end, what we need to do, we need to preserve these models. Instead of saving whole model itself, we need to save the model head. So basically, we are not going to save the model all at once, but what we are going to do, we are only going to save the LoRa adapters with rank 16. No, in this case I use 64. This number has to be changed. And basically, for a future lab, we are simply, what we need to do here is that we load that adapter, and being able to mount it on top of the base models to be able to use that effectively. So with this simple command, we are able to do that and save it in our local repository. In the next lab, what we are going to do, we are going to use this this adapter that we have saved here and mounted on top of the base model to be able to run it locally. So we have learned a lot of topic. It's been a long lab. I assume that at the end of the lab, you would have a lot of information mixed. But I highly encourage you to repeat this experiment that we have done here, and try to examine the code and play around with the number of rank that we have here, which is number 4, 16, and 32. I have already tried with 64. You play with the different learning rate to see what is the impact. Try to visualize the learning, the loss function measure over the different steps. Try to play also with the number of the steps, and try maybe to change the base model. Instead of using LLaMA 3 billion, use I don't know, 𝐶𝐻 2.5, 3 billion Instruct version to see that how it look like and what is the impact of the to the model. And maybe as the last exercise, I highly encourage you to try with the PubMed Q&A dataset using all 3 classes. I try to make this dataset available in the repository so you would be able to play around a little bit with that. So far we have done all the exercise locally in our notebooks, and now the question is that how we would be able to scale that model. Obviously, doctors, they are not interested to work on the Jupyter notebook to get their answer on the biomedical question and answering. They need some kind of interface like ChatGPT. In the next meeting and session, we would be able, you would have a significant amount of information to digest, to be able to run your model locally. I'm looking forward to see you in the next lab, and keep learning and happy learning. Thank you very much for your attention.